Okay, so let's take this previous example that we had and try to generalize it. So what would, the question sort of, what would our guess be for the most general version of the time reversed renewal chain, right? We saw that, the transition probabilities had to kind of be flipped. And so instead of in the original renewal chain example, you go from state 0 out far to some natural number and then deterministically come back to 0. In the time reversed version, you step forward, right, from 0 to 1 to 2 to 3, all the way up to some number, and until, with an unlucky coin flip, so to speak, you're taken all the way back to 0, right? And so in the previous, this matches our previous example, but this coin flip that I was flipping, at every single sort of increment, it had the same exact probability. And it's likely, we can kind of take a guess here at this point. We're just taking a guess that in the general version, where the original renewal chain can go from 0 to any state with an arbitrary probability, not the one that I set up last time, right? The one I set up was a very specific example to ensure that the stationary distribution was was positive, and it existed also. Here we're trying to generalize it, so we had essentially before a coin flip of the same coin, and we would increment our state every single time until an unlucky coin flip, right, landed on tails and we got swept back to 0. Here we're gonna try to pretend that the coin changes in every state. So at state 0, I'm gonna flip a coin that lands on heads with probability p0 and lands on tails with 1 minus p0, right? And then I either move forward if I had heads and stay at 0 if I had tails. And then I repeat the same thing at state 1, but now my probability of getting heads is p1 and the tails is 1 minus p1, and so I go back to 0 with 1 minus p1, right? And then this generalizes to the state n, where the coin flip landing on heads would have probability pn, and 1 minus pn, I go all the way back to 0. So that's a pretty reasonable guess for what the time reversed renewal chain should look like. And one thing that we can now try to do is map this back to the transition probabilities of the original renewal chain. Essentially, we're going to try to get back to something like this. So if you want to sneak ahead, right, if you remember what were the probabilities of the renewal chain, and now I'm going to put a prime there, right? This is, we're kind of time reversing a time reverse chain, right? That's why, the prime there stands for the time reversed Markov chain, but we're starting with already a time reversed one, right? So this is like doubly time reversed. So in any case, these p prime xy's will now represent the transition probabilities for the general renewal chain. And we remember they looked exactly like this. Starting from state 0, you move way out to state little qy, you move right to state y, and then you move deterministically back from any state from state x, right? From state 1 plus y, you go to y with probability 1. Yeah, so this is correct. If you plug in the x in there, right, in the original p prime expression, you will get the probability of moving from y plus 1 to y, meaning going back a step towards 0. That has to be 1. So that's what we're trying to do. We're trying to guess what the general time reverse chain looks like, and then reverse engineer back and try to find a relationship between these q's and these p's, right? These are the probabilities for my coin flips that let me move forward in the time reversed renewal chain, and these probabilities, little qy's, are the ones with which the original renewal chain sends me to state y from state 0. Okay, so how do we work this? And this is very related to what you have to do in the homework. So how do we kind of work this through? Well, one thing to recognize is that the two must share a stationary distribution if they are to be time reversed versions of each other. And if they share the same stationary distribution, they must share the same stationary measure, right? Which we know from our previous lectures is of this form. So I'm going to call mu x, I'm going to denote that by big Qx, which was, if you remember, the sum over the little qy's, right, for all y greater than or equal to x. Right? This expression is what we verified before in lecture to be the stationary measure of the renewal chain, and if that was the case, it must also be the stationary measure of the time reversed renewal chain. And I'm going to assume here for the time being, as we did kind of in the previous lectures, we had to construct this time reverse chain under the conditions that the stationary distribution and therefore the stationary measure mu x is greater than 0, and then I also need the sum to converge to make sure that the stationary measure exists. And you could try to think about what what it means to drop some of these assumptions, maybe even this one, so you can try to work this through on your own if you're interested. But now let's get back to kind of the task at hand. What we're trying to do is construct now the one-step transition probabilities for the renewal chain, starting from the time reversed renewal chain, right? So everything is just moving backwards. It makes it a little bit hard, but hopefully at the end of this you can kind of start with either the renewal chain and construct its time reversed version, or start with the time reversed version and come back all the way back to the original renewal chain, which is what we're going to do here. Right? So we're doing maybe slightly the harder kind of problem. So right, so here we have kind of like two time reversals, right? We're constructing p prime, which is the time reversed transition probabilities, and we're trying to reverse the time reversed renewal chain, and so that's why this is p prime. Maybe it should be p double prime, but just so you keep in mind, these should be the transition probabilities of the renewal chain, and these p's right here are the transition probabilities of the time reversed renewal chain, which we've guessed to be of this form. So now let's just try to kind of plug through here, right? That one benefit of using the stationary measure here again is you don't even need to know the stationary distribution, right? You only need the stationary measure. The ratio is the same, right? The denominators, which are going to be of this form, cancel out, and so these expressions are now equal, right? That's a nice thing to notice, and it's actually used in what's called the Metropolis-Hastings algorithm, but we'll come back to that. So now let's try to actually see if we can plug some numbers in and try to match up the py's with eventually to get an expression for the little qy's. Okay. So let's say I'm trying to get a transition from state x equals 0. Right, we kind of know what that is. In fact, it's got to be this, right? The transition of the renewal chain from state 0 to state y is little qy. But let's try to plug in what these transition probabilities that we kind of guessed tell us. So first of all, when x equals 0, this transition here is py from any state y to state 0. That's just 1 minus py. Right, so that's this part. This transition probability is responsible for this 1 minus py term, right? Just by this definition right here, actually, with the y substituting the x. Then mu y divided by mu x is just mu y divided by mu 0. What's mu 0? Mu 0 is the sum over all of the little qy's, and that's just 1. Right? This is the statement that the renewal chain has to go somewhere from state 0. Right? It can't, it has to go to some state, and so the sum over all the little qy's is 1, and so mu y over mu x is just qy divided by 1, and so I left off the 1. What's this one right here? This is looking for the transition from x equals y plus 1 down to state y, right? And that was always 1 in the renewal chain. What do we get when we plug in these guys? We get so to go from, right, this one is going from y to y plus 1. That's just py, right? The probability of going from y to y plus 1 is little py, right there. And the ratio of mu y over mu x is just qy over qy plus 1, right? Because x is equal to y plus 1, right? And we just use the definition of mu. So that's what you get here. So now what does this mean? This is now, because we know this, right? This is what we want to get in the end. This is establishing for us a relationship between the renewal chain and its time reversed version. All you have to do now is set 1 equal to this number, which is what it should be, right? This better be 1, and this thing better be little qy, right? And so if I set this to 1 and I solve for py, I get that py is equal to big Q y plus 1 over qy. Right? So what do we have in the end? And by the way, right, this is all I need to establish a relationship between the time reversed renewal chain and the original renewal chain. You can also try to verify by yourself that little qy is in fact going to be equal to this expression when substituting for this. Right? So I'll let you work that out. I haven't, but it's got to be right. So hopefully there's no mistake there. There really shouldn't be. I'm solely relying on this having to be 1 to recover my expressions for the PYs. And what I've done now is related the transition probabilities for the time reversed renewal chain, right, the little PYs. I've recreated them in terms of the little QYs, which are used to construct any original renewal chain, right? So when given the QYs, I have a renewal chain. I can now take those little QYs and sum them up to get the big Qs, and then write down what the P's had to be, right? What the coin flip probabilities had to be for me to keep moving forward in this time reversed version. Or if, like in here, in this example, I'm given the little PYs, then I can try to solve for the, right, this is going to be a longer thing, right? But I can try to solve from the little PYs for the big Qs, and then recover the little QYs. That should be possible, right? And the reason is that you can kind of start, you can imagine starting at y equals 0, in which case the denominator is 1, and that one is Q1, right? And so you have that kind of map, and then you go ahead and kind of keep working, and then you can try to solve for the little Qs sort of step by step. But this is enough to establish that relationship back and forth. And so, the summary is here that this is the time reversed version of the renewal chain, and you'll see it in your homework. And there you'll have to kind of do quite a few exercises with both of these chains, and switching back and forth, and being able to kind of deal with each one clearly. So hopefully this helps that part of the homework.